Recording in the cloud. Okay, it's good.
All right, welcome, ladies and gentlemen. It is my honor to introduce Sean Lai from Cornell. Sean is currently a sixth-year PhD student at Cornell, advised by Professor Yi-Hsiang. He received both his master's and bachelor's degrees in electrical engineering from National Taiwan University, and his research focuses on high-level synthesis for FPGAs, programming models, and compilers. Welcome, Sean, and please feel welcome to begin.
Yeah, thanks, Stephen, for the introduction. Yeah, let me share my screen. Yeah. Okay, you can see a screen, right?
Yep.
Yeah. Okay, yeah, so yeah, thanks everyone for joining. And today I'm going to present two programming frameworks targeting FPGAs. And both of them, they adopt the idea of decoupling the algorithm from hardware customization. Okay. Yeah. Then again, you're welcome to interrupt me if you have any question during my talk. Yeah. So to begin with, let me give you some quick background on FPGA. Yeah, so recently we can see a rise of FPGA-based computing, from both ends. For instance, in data centers, we can see Intel, AWS, and Microsoft. They all provide FPGA cloud clusters, and also in edge devices, we can also see an increasing deployment of FPGAs, in many different applications. And the reason why FPGA is so popular is that it can be used as a programmable accelerator. And the main feature of FPGA is that it provides massive amount of fine-grained parallelism. And so, as you can see an example on the left-hand side, this is an FPGA that's being used on AWS F1. Although this is not the latest FPGA, it already provides 2 million logic blocks or lookup tables. Yeah, so if you're not familiar with that, to implement an 8-bit adder, you need 8 lookup tables. So now you can imagine how many additions can be run in parallel with this many lookup tables. And in addition, FPGA also provides DSP blocks, which are hardened multipliers, and it also provides massive on-chip memory bandwidth with these block SRAMs. Yeah. Another advantage of FPGA is because of its you can achieve high performance per watt. But it is also well known that FPGAs are really, really hard to program. And to reason about that, I'm going to use this roofline diagram. Right. So basically, if you think about the hardware acceleration, the key is to run as many things as possible in parallel. Right. So if we want to illustrate that using this roofline diagram, what we're actually doing is that we want to move our design point vertically upward to the roof. Right. So in other words, we are trying to improve the throughput under the same operational intensity. Right. So to achieve that, we can do things like parallelization and also pipelining. As for this kind of optimization, we call it compute customization. And today, our design point can also be on the left-hand side, this is memory bound, right? So to solve this problem, what we can do is we want to move our design point horizontally to the right, so that the maximum throughput is no longer bounded by the memory bandwidth. And then to achieve that, we can use memory banking, data reuse, or streaming, right? So for this kind of optimization, we call it memory customization. And finally, in order to run more things in parallel under the same silicon area, so one can do is by using this low bit width integers, or using this fixed point number. So as you can see on this roofline diagram, what we're achieving is we further rise the compute roof. Right, so now we can achieve even better throughput with this kind of, we call it data type customization. And to implement all these essential techniques on FPGA is not simple. Right, so if we just take a look at this, the traditional way, right? So until now, there are still many people trying to program the FPGA using RTL. Right? But for instance, if you just want to implement a very simple 8-bit counter in very low code, then you need this around 20 lines of code. Right? So this might not be very productive, right? So to solve that, one thing that we can do is we can further rise the abstraction level by using some high-level specification. In this example, we're using this high-level synthesis. Right. When in this case, we're using this C programming. So as you can see, by using this HLSC, we only need 4 lines of code to describe the same 8-bit counter. Right. And another advantage of using this HLS is that you can actually capture all 3 types of hardware customization. Right. So in this case, on the right-hand side, I'm showing you an example and optimize HLSC code. Right here we have all three types of hardware customization being implemented. Right, like we have compute, data type, and also memory. But if I ask you what this code is doing, then it might not be clear to you, right, at first glance. And the reason is that as you can see the hardware customization, they are deeply coupled with this algorithm part. So the algorithm is like being separated, right, throughout this entire program. Right, so it makes it less portable, maintainable, and also less productive. Right, but I can tell you that actually this code is just doing a very simple 2D convolution. Right. So to solve that, like recent work include like Halide and TVN. I believe many of you are already familiar with that, right? But what they are achieving is that they propose to decouple the temporal schedules from part of the hardware customization from the algorithm part, right? So an example is shown on the right hand side. This is like just a very simple Halide code snippet. But as you can see, there are still some part of the hardware customization that are still like coupled with the algorithm itself. So what we want to do, or what we try to do, is we want to further decouple like other hardware customization from the algorithm, right, to make it cleaner and more productive. So in today's talk, I'm going to introduce like two programming frameworks. One is SuSy and the other one is HeteroCL. Yeah. So yeah, I'm going to introduce SuSy first. Systolic array, right? And this work is in collaboration with Dr. Hongbo from Intel, right? And we also have other collaborators from Peking University, Tsinghua University, and also UCLA. So just to give you a quick overview, like what are systolic arrays, right? So basically for all systolic algorithms, they share the same property, that is uniform data dependency. So in other words, all dependence distances are constant. So basically with this property, we can easily map a systolic algorithm to like spatial architectures like systolic arrays. And then systolic arrays is composed of processing elements or PEs. So the one of example I'm showing is on the right hand side. In this case, we have like 3 by 3, which is totally 9 PEs, right? And each PE they process, it processes the data rhythmically, as you can see in this animation. So as you can see, this also provides massive parallelism, which also leads to high performance. And we can actually see that systolic arrays are being adopted like in many important domains. So for instance, like in linear algebra and deep learning, and also like in bioinformatics. And we can also see that they are being deployed on many different hardware, like including TPUs, ASICs, and also FPGAs. So what this SuSy can do is that, first of all, we are productive because, as I mentioned, the key here is we want to decouple the algorithm definition. And in this case, we focus on the decoupling between the algorithm definition and also the spatial, the optimization. Yeah. And then we're also efficient because we can like represent many different optimizations explicitly, like space-time transformation. And finally, we can also like describe a set of systolic algorithm using UREs, which makes our programming frameworks more flexible. Yeah. And in the later slides, I'm going to like delve into the details, like what are space-time transformation and what are the UREs. Yeah, but in general, we can say SuSy is a programming model for constructing high-performance systolic arrays. And there's another reason that I call this tool SuSy, right? In addition to these red characters that I highlight here. So yeah, another point I want to mention is that SuSy is currently now open source, and it is under this Intel's T2SP project. Yeah. So go back to the naming, right? So think about the traditional Japanese cuisine, the SuSy, right? It's usually composed of two parts. One is the white rice, that is the base, right? It's correspond to our algorithm definition. And what makes a piece of SuSy delicious is its ingredient, right? So for example, like the tuna or the cucumber, right? So similarly, like in order to achieve high performance, we need to apply a set of spatial optimization, right? So basically this spatial optimization correspond to this ingredient of the SuSy. And I believe many of you have this experience that when you try to eat a piece of SuSy, sometimes the ingredient just decouple themselves from the white rice. So we also have the same idea that the spatial optimization is decoupled from the algorithm definition. And finally, we usually like eat many pieces of SuSy at a time, just like when we implement a systolic array, it is composed of several PEs. So following, I'm going to give you like more details on how we can actually achieve high performance with these SuSy programming frameworks. But first of all, we need to understand how we build the wise-rise, that is the base part. Right. So for SuSy, we are using this uniform recurrence equation or UREs. And so actually, UREs is very simple. It is actually describing an n-dimensional iteration space with constant data dependence. And if you still remember, I mentioned that all systolic algorithms have this as property, right? The constant data dependence property. So that means by using UREs, we can actually describe any systolic algorithm. Yeah. So just give you like a very simple example, this matrix multiplication. So on the right-hand side is the C code, right? We have like 3 loops, ijk, and k is the reduction loop. Yeah. And on the left-hand side is the corresponding URE code, and it is also very easy to understand. So in this case, in addition to this A, B, these 2 inputs A and B, and also the output C, I also introduced this intermediate variable Z, which is for the accumulation result. And to interpret this select, it's just like an if then else. Sorry. So in this, like in the first line, you can see that when k equals to 0, that means when we start the accumulation, we accumulate from 0. And otherwise, we accumulate from the previous accumulation result, that is when k minus 1, right? And finally, in the second line, we say that after all the accumulation is done, then we return our accumulation results back to the output C. Right. And to describe that using SuSy, we're leveraging the Halide syntax, right, which provide this declarative programming style. So as you can see, instead of directly writing down all the for loops, we can just write exactly the same as what I'm showing in this URE, right? And definitely Halide is not able to support this URE description. That's our extension, right? So knowing how we can describe a systolic algorithm, the next thing that we need to do is how we map it to a physical systolic array, right? So to do that, we need to use this space-time transformation. So basically, what the space-time transformation does is that it includes 2 parts. One is describing how it is mapped to a physical systolic array with this space matrix, and the other one describes how the data are being processed using another time matrix. Right. So just let me use the same URE, this matrix multiplication. Right. So on the left, I'm picking this transformation matrix T. So for now, our framework, we rely on the user to provide the matrix T. Right. So to determine the space dimension, we just need to multiply the space matrix pi with the iteration domain. In this case, we have a 3-level for loop, this ijk. And the result here is I and j. So basically, that means we can map this SGEMM algorithm into a 2D systolic array. So one dimension maps to loop I, and the other dimension it maps to loop j. Right. And then the second thing that we need to do is to determine the time schedule. In this case, we can do it by multiplying the time matrix tau with the iteration domain. So in this case, the result is I plus j plus k. So to interpret that, that means, for instance, if we want to calculate this z00k, then this is being calculated when time t equals to k, right? And then for these 2 values, they will be calculated when time equals to k plus 1. So as you can see, if you still remember, our animation is like this data are being processed like in a wavefront pipeline, right? So another thing that we can do is that we can actually to play with different combination of space-time transformation and UREs to do some simple design space exploration. Right, so on the top, I'm showing you exactly the same systolic array that I shown in the previous slides. But as you can see, so one problem here is that all the inputs that are being fed to different PEs, right? So it is not scalable if we have a very large systolic array. So one thing that we usually do is that we reuse the data from the neighboring PEs, right? So in this case, we need to introduce like 2 new intermediate variables, X and Y, for the reused data, right? So what we're exploring here is actually the trade-off between the area and also the performance, right? So on the top, we have less area, but we have a worse performance due to the broadcasting. right? But for the lower one, we have better performance, but we need, because of the intermediate results, we're actually consuming more area. And another, in addition to this space-time transformation, we actually provided many others spatial optimization, is especially for this what I highlight here, that is the optimization for customer I/O, and they are actually the key to the high performance, right? But for the details, they're kind of like more complicated. So please take a look at my paper, yeah, for more details on what this each I/O customization does.
So Sean, sorry to interrupt. Can you go back one slide? So if I understand correctly, so like the UREs help you separate the different ways you could iterate over a tensor. And then because of that, it makes it easier to express these optimizations.
You can say that, but the key goal of UREs is to describe like more like how the data is being processed, right? So as you can see, like in this slides, right? So basically, by changing different UREs, we can say for the upper one, we're actually broadcasting these inputs, and for the lower one, we're actually reading the data from the neighboring PE. Yeah. But for how they are actually like being calculated, so this is more like the connection between PEs, right? But how these data are being processed, we actually need to use this space-time transformation to determine that.
Got it. And so when we have these kinds of, there's almost like rewrites, which is really nice. But when you get all these optimizations based on these transformations, how do you decide what order to apply them in?
So you mean like how do I apply this order? So usually, like most of them are order independent, right? But
they're just always good. They don't impact each other.
Yeah, most of them, but there are some of them, there are like exception. We need to apply them in a sequence of order. Then in that case, we will need like more the experience on programming this. But so actually the better way is that we're actually thinking of maybe we can wrap some of the optimization together into like a higher level or like a macro, right? So that the user can directly apply that without worrying like the details. Right?
It's almost like, you know, that suggests, you know, like Halide and TVN have scheduling languages.
Right. So this is so they are the same idea.
Yeah, exactly. Got it. Okay, great. Thanks.
Hey, Sean, before we move on, can we back up one slide again?
This one?
I did have a quick question here with respect to area. So you're saying that the top one has fewer intermediate variables, and so it has less area. Is that in an ASIC or in an FPGA? Or are you talking about like the amount of code, like area and code?
No, so this area, like I think it works for both ASIC and FPGA. Basically, they are, it's the same idea, right? So basically, use fewer intermediate variable. That means we don't need to allocate that many memories, right?
Well,
they give the same number of register cells, right?
So
number of registers, yeah.
Does that actually translate to like resource utilization on an FPGA? Because in an FPGA, like a lookup table based FPGA, usually the registers are tightly coupled with the lookup table. So whether or not you instantiate it or not doesn't really affect your resource utilization.
No, so these intermediate variables, they will also be mapped to register. It depends on like how we actually generate the HLS code. Right, so for instance, we can use like shift registers, like in this case, and they will be mapped to register, right? Or if they are like even larger, then they might be mapped to like BRAM, right? It depends on like how we actually describe that, right? But no matter how we actually describe it, since we are using like more this intermediate result, we definitely need to use more data area resource.
I see. Okay.
Yeah. Okay, yeah. So for compilation flow, it is also very straightforward. So basically, given the SuSy program, we lower it to the extended header IR. And after that, according to the backend, we can apply some target-specific optimization. And then finally, we use this HLS flow to help us deploy our design to the actual FPGA. Yeah, so following, I'm going to show you some of our experiment results on these programming frameworks. So first of all, in the next few slides, there will be like 2 boards that are under evaluation. One is this Intel Area 10 board, the other one is the Xilinx View9P board. Right. And actually, these 2 boards, they have what I want to mention is that they have a similar computation power, like in terms of the number of MAC operation that they can do. Right. And although now SuSy we only target this Intel Area board, but it is actually quite simple for us to extend to other different backend like Xilinx board. Right. So the first thing that I want to show is the generality, right, or the flexibility. So basically with UREs, we can describe any systolic algorithm. Right, so in this case, we select the benchmark from different application domain, like we have linear algebra, deep learning, and also like bioinformatics. So first of all, as you can see, SuSy is actually the only one that can describe like all these 4 benchmarks, right? And secondly, we also show that by using only like tens of lines of code, we can already achieve very high performance in terms of like both these lines of code, including like both the UREs and also the spatial optimization. And second, so now I'm going to delve into take a look at using this Smith-Waterman to show you like why SuSy is capable of actually describing this high flexibility. And so first of all, Smith-Waterman is an algorithm for describing the genome sequence alignment, right? And as you can see on the left and bottom left, I actually plot the data dependence when we trying to calculate using this Smith-Waterman. So as you can see, the middle cell is actually depends on the left cell, the top cell, and also the top left cell. Right. So as you can see, the parallelism actually lies within the anti-diagonal direction. Right. So in this case, it actually means that in order to achieve a high performance, right, in order to explore the parallelism, we actually need to skew the iteration space to make it align with this anti-diagonal direction. Right. So with that in mind, we can actually take a look at how other programming frameworks, right? So for instance, like for T2S tensor, you can the reason is that you can only like support very simple kernel similar to matrix multiplication, and it also does not support space-time transform, so that it is not able to describe this skewed iteration space. Yeah. And as for PolySA, although it provides some preliminary support on this space-time transformation, but it lacked the support for dynamic control flow, which is an important part for this Smith-Waterman algorithm. And finally, for Spatial, it is like a general programming framework, right? And the problem of Spatial is that it does not have a way to concisely describe like how we can map to a systolic array. Right? So if we compare with the Spatial, we can see that because of the difference of targeting or not targeting systolic array, we can achieve like higher performance and also like higher frequency, right? The next thing that I would like to show is that if we just focus on like the traditional systolic array benchmark, we can actually achieve the same level of performance, right? So for instance, here I compare with this Ninja HLS, which is like the manually optimized HLS code. So as you can see, by using only like 30x fewer lines of code, we can already achieve like 86% of throughput. And if we compare with other like state-of-the-art systolic array frameworks like PolySA and T2S tensor, we can actually achieve like the similar frequency, throughput, and also DSP efficiency. So finally, let me use this spider web or this radar chart to do a quick summary. So first of all, if we compare with this programmable control, HLS definitely has the highest programmable control, right? But SuSy also provides just a little bit lower programmable control because we can actually use a set of spatial optimization, right, to make our systolic array high performance. As for the portability, since we're using this DSL like using this like the extension to Halide, right? So actually we can easily portable to like other devices, right? And HLS is definitely very target specific, right? As for the performance, as I've shown in the previous pages slides, that we can achieve like same level of performance as HLSC and other state-of-the-art systolic array frameworks. As for generality, because we support UREs, so we can describe any systolic algorithm. So we are just less general than like other general programming frameworks, including HLSC and Spatial. And finally, for productivity, because this decoupled programming style, right? So basically, we are just a little bit lower productive than PolySA, which provides a one push button compilation flow. So finally, if we look back on our roofline diagram, what this SuSy achieved is that for the compute part, we have these UREs and also space-time transformation to describe how they are being computed, right? And for the memory part, we also provide a set of IO optimizations for the people to achieve higher throughput with this memory customization, right? Yeah. And again, we are currently open source on GitHub under this Intel T2SP project, right? So before I delve into, I go into this HeteroCL, is there like any other question on SuSy?
You mentioned that PolySA cannot handle dynamic control flows. I wonder how do you SuSy handle those cases?
So basically, the difference is that with SuSy, we are actually using these UREs, and UREs can support this dynamic control flow. So basically, that's enabled by the UREs, right? And then for PolySA, it's more like the restrictions on the compiler itself. Because like for
any restrictions on the syntax of URE, I mean.
So for instance, for PolySA, what it takes in is like a C code, right? So for C code, you can definitely describe dynamic control flow, but the problem for PolySA is that its compiler does not recognize, or it cannot like accept this dynamic control flow, right? And as for us, although we're not using the C programming, right? But with UREs, we can also describe this dynamic control flow. So basically with UREs, we do not like introduce like other limitation. Right?
Okay.
Yeah.
I have a quick question on the frequency. What tends to be the critical path in a lot of these systolic arrays that you're generating?
Right. So I think for this frequency, like most of the time, since first of all, since we're using this high-level synthesis, right? So instead of directly writing the Verilog code, the RTL code, right? So usually the frequency is determined by how good the HLS tool is, right? Mm-hmm. So another thing is that for this Ninja HLS, why they can achieve this high frequency is that because this code is being written by like the HLS experts, and so basically they know how they can like play with the HLS code in order to affect like the real like place and route of the underlying tool. Okay.
Sure. Yeah, I was just kind of curious, like in your specific architecture, do you happen to know what the HLS tool, like what ends up being the critical path? Is it inside the memory subsystems? Is it inside the like GEMM, the processing elements?
Yeah, we did not like take a look into that part. Yeah.
I see.
Yeah.
Okay.
But I think like most of the time the place and route part is like the most critical. So basically how good your design is being placed and route, then that's basically the one of the main issue there.
Are there pragmas in the HLS languages that allow you to dictate the floor planning?
There's no, but sometimes you can, for instance, you can hint the compiler to insert some of the register in some places, right? So that they know that, oh, maybe, for instance, it's more like introduce another pipeline stage, right? So that they have like more flexible timing, right?
I see.
In cases, yeah. Okay, so yeah, then if there's no other question, then I'm going to talk about HeteroCL. And I also believe like many of you've already heard HeteroCL before. Right? So this work is in collaboration with like Yu Wei and Yuan, which are my colleagues from Cornell, and also Jie Yuzhe, Cody, and Professor Zheng Kong from UCLA. So HeteroCL is like a more general programming framework compared with SuSy, right? So basically SuSy only targets systolic algorithm, but HeteroCL is like a general programming framework for FPGAs. And we also have many features. First of all, we are flexible because we provide like a mixed declarative and imperative programming style. And secondly, we can also like map to spatial architecture template efficiently by targeting, for instance, systolic arrays, right? And finally, we are with this decoupled algorithm and hardware customization, we are also portable. Right? So we are also like currently open source on GitHub. Yeah. So following, I'm going to show you like how HeteroCL can like actually like cleanly decouple like all three types of hardware customization. Right? This is an essential technique for hardware acceleration. Right? So first of all, with this compute customization is actually quite similar to what TVN already provided, right? So on the right-hand side is the C code, and on the left-hand side is the HeteroCL code, right? So if you're familiar with TVN, then this code snippet is also like should be familiar with you. You should be also familiar with this code. Sorry, yeah. So as you can see, we are using this declarative programming style that is based on TVN, right? And similar to TVN, we also have this scheduling function, right? In this case, we call it that this decoupled customization. Right, so we have this .speed, .reorder, these are already provided by TVN, right? But more interesting, what is more interesting in HeteroCL is that actually we also decouple other type of hardware customization from this algorithm part using the same like concept, right? So the first thing here that we can do is we can decouple the data type also, right? So for instance, like in this as you can see on the code on the left hand side, we are also using this gray scheme and also quantize. We can actually quantize the data right into a fixed point number, right? And what we can actually achieving is so for instance, given a 32-bit floating point, we can quantize or downsize it all the way down to a 2-bit integer, right? So as you can see, by doing this quantize primitive, we don't need to change the algorithm part, right? So similar to in what we have done for this compute part, right? This .split, .reorder, we can also use this quantize to achieve the similar result, right? But this one is just for data type. Yeah. As for memory, we can also apply this kind of same trick, right? So why memory is important is that actually in order to really achieve high performance, we actually need to increase the on-chip and also off-chip memory bandwidth utilization, right? So in this case, given like this 2D convolution, right? So one common practice on FPGA is that we can actually introduce like reuse buffer for this data reuse, right? So as you can see, if we compare like two consecutive execution of this 2D convolution on the y-axis, right? We can see that there's actually many pixels that can be reused, right? So what we can do is like by introducing this line buffer to store the data that can be reused, right? So we don't need to access the image as it every cycle. Right? So in HeteroCL, what we need to do is by using this .reuse as primitive, right? So again, we don't need to touch the algorithm part because now we cleanly decouple this memory customization from the algorithm, right? And similarly, on the x-axis, we can see there's also all the data reuse, and we can introduce this by using this window buffer. And in HeteroCL, what we need to do is just to apply another reuse set, right? And then finally, with the combination of this x and y axis, this data reuse, we can actually achieve high performance or high on-chip memory bandwidth. So currently, we, as you can see, we actually support many different types of hardware customization by using this rich set of primitive provided by HeteroCL. And in addition to this, like this micro, right, primitive, we also provide some macros, right? So basically, it helps the user to map to architecture templates, spatial architecture templates. So currently, we're relying on like two backend frameworks. One is SODA, developed by the UCLA, and with this SODA, we can actually map a stencil application into this data flow architecture with line buffers, right? And then similarly with the systolic array, we target AutoSA, which is like the following work of PolySA, right? And now since SuSy is also open source, we can also target SuSy by ourselves, right? And another thing that I mentioned previously is that with this HeteroCL, we are very flexible, right? And the reason is that we, instead of like using this, in addition to that, the decorative programming style like provided by TVN, right? We also provide this imperative DSL. So as you can see on the right-hand side here, I'm using this HCL.4 to describe the same 2D convolution kernel, right? And the good thing of HeteroCL is that we can actually apply the same set of customization primitives to our imperative code as well. So our compilation flow is also quite similar to SuSy. So basically, given the HeteroCL program, we lower it to the intermediate representation. But the difference here is that we can actually like target other frameworks, right? Compilation frameworks like AutoSA and Soda to help us further generate like high performance spatial architectures. So I think this result is not new. It's because it's like public, like published like 2 or 3 years ago. But what I'm going to show you here is that we can actually describe a rich set of computation kernels, right? And using HeteroCL, and we can actually achieve a quite good speed up, right? But actually what we are capable of doing now is that we can actually use HeteroCL to describe a complete application, right? So in order to do that, there are many things that we need to take care of, right? So first of all, for instance, we need to, like this optical flow, this design, as you can see, it is composed of several small kernels. Like in this case, we have 1D convolution and also like dot product, right? But then now the main thing that enable to describe this complete application is that we need to be able to specify like how the data is being placed and moved, right? So in this case, the input video frames and the output vector, they are placed on the host DRAM, while the other computation that happens on this FPGA accelerator, right? So to achieve that, I'm working with my colleague Yi-Hsiang to actually to achieve this goal, right? And unfortunately, like this work is still like under submission, so I could not like give you too much detail, but I can just quickly give you a taste of what it is capable of, right? So for instance, if you take a look at this code snippet on the left-hand side, but similar to that, like other primitives that I presented, right? So in this case, we also have this decoupled programming style, right? By using this .2 to specify the data movement, right? So in this case, the first .2 says that we want to move the input image from the host to the accelerator, right? And then finally, we want to move the output back from the accelerator to host, right? And we can also have the support at different granularity. For instance, we can also specify data movement between kernels. In this case, we will instantiate like a FIFO between on-chip kernels, right? And another advantage of this .2 primitive is that it can actually combine with other existing primitives like the data reuse and also like this quantization, right, for data type. And as expected, if you want to implement the same thing, like at the same optimality on this HLSC, then we need to spend a lot of lines of code, and it is not very portable and also maintainable, right? And similarly, even like with this, like this HLSC codes I'm showing you here, to describe the data movement between the host and accelerator, we actually need to apply a set of vendor-specific directives, right? So as you can see, we're using a lot of Pragma HLS interface and things like that to achieve that, right? So with HeteroCL, I can give you a taste on what we have done. So for instance, with this optical flow, first of all, we can easily target different FPGA. In this case, we can target like Xilinx and Auto Intel board, right? And in addition, we can actually achieve similar performance compared with manual optimized design from Rosetta, right? So you can see that for the runtime, we are at a similar level. And for lines of code, like unsurprisingly, that we only use like only like 1/3 of lines of code, right, to achieve like the same level of performance and even better portability, right? So if we compare with other existing work, like HeteroCL is actually the only one that can fully decouple all 3 types of our customization, right, from the algorithm part. And secondly, we are only one that provides like the mix, right, declarative and imperative programming style, like we have this DSL, right? And finally, we also can target like a complete application, right, for FPGA. So if we go back and take a look at this roofline diagram, right? So for compute part, we actually can do similar to what Tivian does, like the loop transformation, but we also provide other that are more FPGA specific, like the pipelining part, right? As for the data type, we also have this data quantization that is decoupled, right, from the everything part also. And for memory, we also have this data reuse for user to generate high performance on-chip reuse buffer, right? And also they can specify data placement with our latest this .2 primitive. So again, HeteroCL is now like available on GitHub, and we actually have already have some industry partners that are using this HeteroCL to implement some of their accelerators. Right. Okay, so yeah, finally, I'm going to give you like a quick summary on these two programming frameworks that I talk about today, the SuSy and HeteroCL, right? But both of them, they share some of the property. For flexibility with SuSy, we're using this uniform recurrence synchronization or UREs, right, to concisely describe like any systolic algorithm. And as for HeteroCL, we provide this mixed imperative and declarative programming style, right? And as for productivity, SuSy and HeteroCL, they both adopt the same idea of decoupling an algorithm from hardware customization, right? And for performance with SuSy, we actually provide like space-time transformation and other like I/O optimization primitive, right? As for HeteroCL, we also can target like spatial architecture template by relying on like other compilation frameworks. Right. So yeah, I think this is the last slide I have. Yeah. So yeah, any questions?
I had a question. This is a great talk, by the way. I was curious about what's the largest designs you've pushed through?
You mean the largest in terms of?
Yeah, like have you like tried filling up a really big FPGA with some of the systolic designs that you've generated? Does it scale that well, or is there additional work that you'd have to put in?
Yeah, for SuSy, we actually can like target like a quite large systolic array. I think I believe it's like the input size is like 1K by 1K by 1K. Yeah, and then the systolic array size. But for the systolic array, it's limited by how much like power resource. That's maybe I have that. Let me try to show you. Yeah. So as you can see, actually for systolic array, it's limited by the number of the hardware module, in this case, the DSP provides, right? So we can actually use this to see like how good a compilation framework is, right? So actually we can almost fully utilize the on-chip resource with SuSy. Right?
Cool, very cool.
Yeah, I have a question. In HeteroCL, you use something like HLSC as a programming language. Why don't you directly emit Verilog code?
Yeah, this is a very good question. Yeah, so I think one thing is what HLS can do is actually, so as you can, maybe let me go back to these slides. Right. So basically the difference between HLSC and this RTO is that actually going from this HLSC to RTO, what we need to do is, this is basically an untimed language, right? So basically there's no clock and things like that. And with this RTO code, it is timed, right? So basically what we actually need to do is to do the scheduling part, right? So basically we need to schedule, for instance, which operation should be computed in which cycle. And this scheduling problem is actually non-trivial, right? So if we directly generate RTO code, we can now like achieve, like basically compete with like the latest, like the commercial HLS tool, right? So basically they have a lot of experts that can really generate this high performance RTO code, right? Yeah.
So basically you use HLSC's say time series scheduling part.
Right, and basically another part is, as I mentioned, so that's basically logic synthesis, right? And another part for this, what they need to do is actually this placement and routing, right? So basically, since it is their board, right? So they are the one who most familiar with their board, so they know how to generate like efficient RTL code for their placement and routing. Right? So basically, they have some of their like this in-house knowledge. So on this part, right?
Nice.
Are there any other questions?
So Sean, if you could make one change in the way application programmers write their code for mapping to these accelerators, what would you change?
You mean like for which, like for HLSC or like for the
So, you know, you're basically able to generate these accelerators and find these, you know, optimizations in them. But at the end of the day, right, like I have some program that a person wrote, and I want to make that faster using these accelerators. And so there are challenges with finding that correspondence.
Right, right.
Is there anything that you wish application programmers would do differently to make your life easier?
So actually, that's quite hard to be honest. So basically, it's really hard to ask a software programmer to write high performance things on hardware because they are just not used to that and they don't know how to do that. And so what we're doing right now is that we want to solve this problem by, for instance, like our tool should be the one who gives you the suggestion, right? So basically, we can suggest you like which part of the program can be optimized, right? And also like how you can optimize it, right? So basically, we don't rely on the user to do that, but we can actually give them some suggestion, or sometimes with some trivial part, then basically we just do it for them, right?
How does that work? How do you find those changes?
So for instance, for a simple one that we can do some static analysis, for instance, by relying on like polyhedral analysis or other thing to like analyze the data dependence, right? And then for other parts, we can, for instance, we can do some like runtime analysis if it is like a data dependence, right? So basically we have some dynamic control flow that we can, for instance, emit the traces or other, there are many ways to do that.
This almost suggests more compiler passes or even a JIT though, right? You can imagine the hardware doing this for itself eventually, if you're doing this sort of runtime based analyses.
Right, but eventually we still want to give the user some control, right? So basically, usually the user is still the one who knows the best for their program, right? So I think we still want to give them some control, not we do everything by ourselves automatically. Yeah.
Okay, well, if there are no more questions, let's thank Sean once again.
Yeah, thank you. Yeah,
Thank you, Sean, for coming.
Yeah,
Appreciate it.
yeah.
I'm going to stop the recording. Thanks, everybody.
Thank you.